So we are at the last presentation now, and I give the floor to Florian. And as I mentioned before, he's a PhD candidate at the University of Geneva in environmental sciences. And let's see what happened the last 500 million years. Floor is yours.
Thank you very much, Atina, and thank you everybody for being here. I'm going to speak about what happened. Well, no, not really what happened in the last 500 million years, but how we transitioned from an old system that was not open to something fully open as a QGIS plugin. If you're interested more in plate tectonics and the results of this, I encourage you to attend tomorrow's presentation in the academic track. Here, I'm mostly going to speak about the transition, but first, just want to know if, has anyone heard about paleogeography? Raise your hand, yes, a bit. I guess you have seen those maps of how the continents moved across time, but in fact, paleogeography is very interesting to study some things that happen today, including the results of the 2024 election in US presidential election in Alabama. So for instance, you see that there is this pattern of that blue line, which is where people mostly voted for Kamala Harris, whereas the rest of the state voted for Donald Trump. And in fact, you can link it back to almost to 120 million years back in time. Because if you look at the census data, this is from 2016, you see that the majority of the region who voted for Kamala Harris are of majority African American ancestry group, which can be also linked to the percentage of the slave population within this district in the 1800s, which is correlated to the fertile land that you have in the States, where you had most of the farms which had slaves working there. And this fertile land was actually a result of a coastline that was there in Alabama 120 million years ago. So a lot of sediment influx from the continents to that coastline, which created fertile lands and can partially explain what we observe here today. So this is quite interesting. And if you want to learn more about how we create paleogeographic maps, come tomorrow. I'm going to give here a few examples of plate tectonics and paleogeography solution that exists, and how GIS is or is not so much a part of these workflows. The first example here is the G-Plates software, which is a 3D standalone and open source software that allows you to move the plates back in time and to their past locations and understand the large-scale geodynamics. It's a very interesting software, but it does not allow to create paleogeography. So with sea level, with continents, and with elevations. It's just about the plates. But it's a very good example of an open source software in that domain. Then you have more funky ones, including this from the PaleoMap project. And this is done using Adobe Photoshop. So you basically take a map of, like this is China, a geological map from China, which you delineate by hand typical rock formations. This is, for instance, limestones, connoting a very shallow environment like lagoons and reefs and so on. Then you digitize it using Adobe Photoshop, and then you put it in G-Plates, which will split your PNG file. This is a PNG file, and move it back in time to the past location. This is approximately 300 million years ago. So it's kind of GIS spatially explicit, but it's just drawings and just moving things like splitting based on present day observations. Another more spatially explicit, interesting software is the QGIS Terra Antica plugin, which basically allows to have fully quantified maps of the Earth past topography and bathymetry, but it's based on present-day topography, e-topo, and also bathymetry, which is input in G-plates and moved back also in time. So you have maps with past locations, but with present-day topography, which has its limits, and you need to manually edit it. So the software that we have developed comes from the Panalysis model, which is what we call a dual control approach, which takes present-day geological evidence, not topography, and move it back in time. Not only that, as other software that we have seen, but geodynamically, the reconstruction need to be coherent. So this reconstruction here will be influenced by what happened there and will influence what happens there, and so on. So you have geodynamically coherent. You cannot just switch things between reconstructions as other software do. And we have constantly evolving versions, working on releasing them because it's a very time-intensive process. You have more than 100 and 1,000 features that are drawn by hand. And from this, we can derive fully quantified paleogeographic maps of the Earth past. How do we do it? We first take the model input, the lines, which denote typical geological environments that control the topography. More on this tomorrow. We create nodes, so points with a typical synthetic elevation, which we then interpolate in a paleo digital elevation model. And we then pour into that synthetic topography the oceanic volume, the oceanic water of the present day with the present day volume, and this then allows us to delineate the coastline and what is above or below water. The problem is that this software was developed in 2013 to 2015 and was never released, was using ArcGIS, and the results were never shared. So when I arrived and started my PhD more than a year ago, the first task was to actually try to run it, to make it run again. A few problems about this. It was that when I received the code firsthand was a PDF with like 200 pages or something like that, 32,000 lines of code, not organized. We could not run it because it was developed using ArcGIS 9 up to 10.2 versions, which are no longer supported. Moreover, it was developed in Visual Basics for .NET, which before started didn't know even existed. And I'm not sure this is the best for geospatial. And also, since 2015, where the software was stopped being used, there was modifications to the output data. But in the meantime, in the 2 years where it was developed, you had multiple versions for input data, documentation, and also the code that I received was, I'm not sure it was the correct version, but all of this make it very difficult to assess the end results. Why is this correct? Is this not correct? And this is the topic of my talk tomorrow again. So just to show you, I was able to find a bit of the code and try to organize it in a better way, but still not able to run the code. And then I wanted to compare what was in the code to the user documentation, and these two did not really were not coherent. So something that was written here, like we do this like this, was not coherent with what I was seeing in the code. And you even had some commented parts of the code that were doing other things. And when I tried to also assess the results that were published with the paleogeographic maps, nothing was matching. So it was really a hell of a process. So yeah, this was interesting. So the first task to actually conduct when I started was, okay, is Visual Basics for .NET a good solution? Of course, the answer is no. And you even can see that the language use, actually, this is a Google Trend search from 2004 onwards. You see, even when this was developed in 2013, was quite low. compared to Python, which is on the rise. And so first clue not to use Visual Basics for .NET, but also what software should we use? And we decided to use QGIS because the documentation for developing a QGIS plugin is very nice. And this is an interesting paper that was released this year and shows how QGIS is more and more used. Well, this is still also Google search trends, but you can see the interest is rising and it's reaching ArcGIS levels in the last 4 or 5 years. So interesting. So also, as we wanted to make it open, this made it a very obvious choice to go to QGIS. The problem is that, as you have seen, it was a very heavy software, over 30,000 lines of codes, and many tools were used, including a tool for interpolating from points to a raster, a global raster. And originally, the method that was used in ArcGIS was a natural neighbor. And when I asked, why did you choose this one? They just say, oh, it was creating good looking maps. So, okay. And in QGIS natively, you don't have natural neighbor. You have a Saga extension, but it takes a lot of time to process. So we wanted to know what could we use to interpolate a global raster for topography, so bathymetry and also elevation on continents, based on irregular nodes. These are the nodes from the model for the present day reconstruction. And so also we wanted to know if open source solutions available in QGIS perform better than ArcGIS natural neighbor method. So what we did is that we, instead of taking the modeled elevation, we sampled these nodes with real world elevation from eTopo. And then from these real world but irregularly distributed points, we tested several methods to interpolate a raster on the global scale. And then this one we subtracted with the original eTopo to see how it performed in terms of absolute elevation, pixel by pixel, but also with terrain variation using the terrain ruggedness index. And this is what you see here, quite interesting results. This is the standard deviation for absolute difference between eTopo and our interpolation, so the actual elevation value. And this is for terrain variation using the TRI. And it's interesting to note that the best method is the QGIS Triangulated Irregular Network, which performs better in both. And you have nice performance also from ArcGIS solutions. And then you see other solutions that perform a bit a bit worse. So this is why we decided to actually choose QGIS TIN to interpolate in our new QGIS plugin. Also, what we wanted to know is how efficient are these reconstructions from each of the different interpolation methods able to depict the oceanic volume, so below the zero elevation, because understanding the oceanic volume helps us understand how sea level change and how much water we need to add to actually reach that reference volume. And this is very important in reconstruction of the Earth's past, as we have variations in sea level. So this we try to do, and this is really just by using the eTopo nodes with eTopo elevation. So this is the oceanic volume, and are all the solutions that we tested, and inverse distant weighted with nearest neighbor search, bridging, natural neighbor, nearest neighbor, triangulated irregular neighbor and network, and topo to raster. And you can see that they are absolutely large gaps in some of the methods, and TIN performs the second best after the topo to raster. This is from ArcGIS. And what does that mean for sea level increase? This is enormous. The uncertainty are enormous because this is how many meters of sea level you need to add to your map to reach the reference volume. And so here you can see that these two perform very, very badly, up to 250 meters, which is more than what has happened over the last 500 million years. The maximum is approximately 250 meters. And TIN is again the second best after the topo tracer, but still almost 50 meters of sea level that you need to add. So it's a very, very high uncertainty that we're able to quantify here. We published a paper. Well, we submitted a paper. It was rejected. So if you know a journal that could publish this result, please let me know, because we're looking for an alternative now. A few lessons learned. So this shows you a quite good example of transition to open source. But the biggest hurdle in the beginning was not to find technical solution and to find what tool is best, but this was to convince the team that we do not need to use ArcGIS. We need indeed to switch to open solutions. So the mentality shift was the first hurdle that we had to face. Again, for the QGIS plugin, very nice documentation and other tools that are used in QGIS. However, if there was one issue that could be enhanced, is the other external, like when you want to add an external library to your QGIS plugin. This is sometimes difficult to package together. So it would be good to have a discussion later on about this. As I showed you for the interpolation, it's a long process to quantify the differences of the various tools and try to find equivalent tools. So I don't know if this exists, but it would be great to have like a catalog of differences and maybe take user by the hand to show them that if they want to transition to an open source tool, these certain capabilities can do the same as what they're used to in ArcGIS, for instance. One word on LLMs, very useful to understand what the code was doing before. For instance, with the 32,000 lines of code, sometimes very difficult to see what was there, but it's not so good at generating code, although it can help, but it gets confused quite fast. And the last one is, as I showed you in the first slide with Gplates, which is a software that does 3D and spherical movements. It would be good to have this in QGIS because, for instance, when you interpolate, the raster edges are not so good and they do not take into account what is on the other side of the map, which is in reality just closing because the Earth is round. So this would be very nice. I don't know if this exists already, but it would be good to know this. The results is a QGIS plugin, which you can find here, all the links. It's currently in review on the Journal of Open Source Software. And when this will be published, we will publish also in the GitHub plugin repository. And then just on the future, to end my talk, this is the next steps that we're considering. So here on the bottom, you see what I showed you, the paleogeographic maps, and we have other maps like about the thickness of the different Earth layers, the hydrothermal penetration depth, and also the age of the oceanic seafloor. And these are all products that we have created, and we are considering, and we started to create this Paleo Data Cube, because I'm in the team of Greg Giuliani, who actually developed the Swiss Data Cube. And we want to do a data cube for the Earth's past over the last 500 million years or so. And so one way to do it that we're starting is to actually create different products. So as I showed you, and with the two spatial components. So you have the possibility to query this like this, or for the seafloor age maps, for instance, you can do time series for a few selected layers or the entire series to actually query it from WMS. And also to do like time series on a given point here in the middle of the Atlantic, and to see all of these collections, seafloor, paleogeography, seafloor, lithospheric, sorry for the resolution, the crustal thickness, and so on, and how it's evolved through time. How we did this is implement a GeoServer with image mosaic, so one per product, that I showed before, which yields 225 maps with 45 image per mosaic, so 45 timestamps back in time for over 1 billion pixels. We also implemented a catalog with a stack with 5 collections, one for image mosaic linked to our GeoServer. And the ISO norms for time doesn't go back 500 million years in time, unfortunately. So what we did is just to tweak, to do a fake time. So the first digit of the year is 2000, and then it goes to the three digits here for the million years. So like 120 million years back in time would be 2120 million, but we also have the good geological age. And we're going to share in GeoNetwork, kind of difficult for now, but work in progress. So the presentation before was nice to see. All right. Sorry, just the conclusion. So this is very academic example of the transition, and it's funny to see that it's often theorized. Like you have governments, you have universities promoting open science, open source principles, but in practice, it's not often the case. I'm the only one, for instance, in my department, actually doing things like that, and oftentimes it's just put aside. And it's good to see almost that you still can advocate for this and you see encouraging trends. Again, I would really like to see use equivalent open tool catalogs with performance comparison. This would be nice to see. And if you have any ideas to improve the sharing, the data sharing through the Paleo Data Cube, please let me know, because it would be nice. And you're more than welcome to see the presentation tomorrow at 11. So thank you very much.